Warning: hydrazine is toxic and corrosive. Potassium azide and calcium nitrite are toxic. Hydrochloric acid and potassium hydroxide are corrosive. Wear gloves when handling them and only perform reactions involving hydrazine outside. Hi guys, here is MIH. It has been really 2 or 3 months since my last post, and that is because I had quite a few failed projects and I'm simply too busy attending summer schools and preparing for my college application. But today, this first video is going to be a massive success as I prepare potassium azide and potassium metal from domestically available chemicals like hydrazine sulfate, nitrite, and N-butanol. Although the diazotization reaction of hydrazine has been done by many people before on the internet, the reaction is known to be dangerous due to the toxicity of hydrazine and azide. To address them, this video features some unique designs and procedures referenced from the powerful handbook, Small-Scale Synthesis of Laboratory Reagents, that minimizes risks while greatly shortening the reaction time from the usual half a day to just under 2 hours. Let's get started. The synthesis features 3 separate parts: the synthesis of N-butyl nitrite, hydrazine, and potassium azide. Of course, if you count in the final step of attaining potassium, that's 4 parts. A 500 ml flask is placed in an ice water bath, and a solution containing 47.2 grams of calcium nitrite and 100 ml of water is added. Sodium nitrite is no doubt the more popular and commonly available alternative, but all I had on hand was calcium nitrite. 60 grams of N-butanol was then weighed and added to the flask. Although N-butanol is soluble in water to an extent, it is not miscible with the concentrated nitrite solution. Some people prefer other alcohols such as isopropanol or amyl alcohol, and I'll discuss about this choice of N-butanol later. 150 ml of not so pure 20% hydrochloric acid, previously chilled to 15 degrees C, is added to the dropping funnel. Despite that many procedures claim that cooling to 0 degrees C is necessary to ensure good yield, I still obtain a fair amount of product even if my reagents are only chilled slightly. Very strong stirring is started, and the acid is slowly added to the flask. To my surprise, not even traces of nitrogen dioxide gas evolved, and nothing seems to happen. I added the acid even faster, but still no gases are seen. After around 2/3 of the acid is added, the cloudy water phase clears up, and the characteristically yellow oil phase of N-butyl nitrite can be seen, confirming that a reaction did happen. The remainder of the acid is added, and the biphasic mixture is poured into the same dripping funnel to separate the layers. The bottom water layer contains quite a lot of calcium chloride and serves to force more N-butyl nitrite to separate out instead of dissolving in the water phase, as well as pull remaining water from the organic phase. This is an advantage, as no more drying of the nitrite using sodium sulfate is required. The separation was complete, and the N-butyl nitrite is drained in a beaker. Its mass of 70 grams represents an 105% yield, suggesting the presence of impurities, but it can be directly fed to the next step without further purification, such as distillation. After the N-butyl nitrite is done, the other main ingredient, hydrazine, is prepared. This part can be completely skipped if you have access to 80% hydrazine hydrate, but obviously that is nowhere close to being domestically available. If you have some luck, you may find hydrazine hydrate as liquid reducing agents from precious metal refinery sellers, but be sure to ask them what the specific contents of it are. On the other hand, hydrazine sulfate is much easier to buy and to make from domestic reagents such as urea and bleach, with the additional advantage of being non-volatile, so it is chosen as the source of hydrazine. Now, some of you may wonder if directly distilling out hydrazine from a mixture of hydrazine sulfate and alkali would work. The answer is yes, but only at a high temperature enough to destroy borosilicate glass. Thus, an alternative approach is taken here. Start by weighing out 67.6 grams of hydrazine sulfate and grind it to a powder. My hydrazine sulfate contains a bit of moisture, so it is not a free-flowing powder, but that's fine. 76 grams of 85% potassium hydroxide is weighed and also powdered, this time being much more annoying due to its hygroscopic nature. The hydrazine sulfate is added to a conical flask and brought outside to prevent me being killed by hydrazine vapor. The not so finely powdered potassium hydroxide is added to it in small portions. Simply shaking the flask will allow the two chemicals to react and produce hydrazine in addition to potassium sulfate and water. Nothing seems to happen yet, but as more potassium hydroxide is added, visible liquids consisting of hydrazine and water begin to form, and the mixture clumps together. When this happens, adequate mixing with a glass rod is necessary to prevent sudden runaway reaction when a lot of potassium hydroxide contacts with the hydrazine sulfate at once, which is what is happening here. I didn't realize that reaction is so exothermic, and some hydrazine vapor is released from the flask, which, needless to say, is very dangerous. I'm wearing a respirator and gloves at all times during this procedure, so fortunately I didn't smell any hydrazine. I took the lesson and used a water bath to cool the flask down, and continued adding the rest of the potassium hydroxide. When all of it is added, some ethanol is added to the beaker and then poured into the flask to dissolve the hydrazine from the insoluble potassium sulfate. You may imagine it would be easier to dissolve the potassium hydroxide into ethanol first and then add hydrazine sulfate, but the precipitated potassium sulfate is gel-like and traps a lot of hydrazine. Mixing the two solids directly can avoid this loss of yield. The slurry is diluted by more ethanol, shaken by hand, and filtered. The filtration, although still slow, is faster than expected. A total of 240 ml of ethanol is used in all of the washings and dilutions. Finally, a slightly cloudy solution of hydrazine hydrate and ethanol is obtained. With both N-butyl nitrite and hydrazine ready, the main dish of potassium azide can finally be made and served. 26.6 grams of potassium hydroxide is weighed out and dissolved in the hydrazine solution. Under strong stirring, potassium hydroxide dissolves rather quickly. A large apparatus is then assembled above the flask, consisting of the same dripping funnel filled with all the N-butyl nitrite and an efficient condenser. The nitrite is dripped rather quickly into the flask, and a white fume of potassium azide immediately appears due to the reaction between N-butyl nitrite and hydrazine in the vapor phase. This fume indicates that the reaction is successful, but it is also very dangerous due to the very small particles of azide that might be breathed in. The reaction is also quite exothermic, and some liquid, perhaps ethanol, can be seen condensing on the sides of the flask. Note that ethyl nitrite may be produced from a transesterification reaction, and due to its very low boiling point of 15 degrees C, it escapes out of the condenser as a gas and carries out the azide fume. I placed a piece of glass on the top of the condenser to block the fumes from releasing. After all nitrite is added, the heating is turned on to bring the mixture to reflux for around 10 minutes, which is said to improve the yield by a few percent. Even at reflux, the content in the flask is still cloudy due to the limited solubility of potassium azide in the ethanol-butanol mixture. As soon as the stirring is turned off and the boiling stops, all of the azide settles to the bottom as small white crystals. I decanted the supernatant to another beaker to see how much azide dissolved in the solution. As the solution cooled, gorgeous flaky crystals of potassium azide slowly separate. To be honest, these crystals are probably one of the most beautiful ones I've ever seen. After cooling to room temperature, the crystals are filtered off and weighted to be 6.93 grams. The crystal in the flask is filtered as well, and their mass is 11.61 grams, which renders the total yield to be 18.54 grams, or 60.2% based on hydrazine sulfate. A discussion about optimizations will be included afterwards, because right now, I'm going to make some potassium. Unlike sodium azide, which decomposes readily when in contact with flame, potassium azide melts before it decomposes, which renders it much safer. Still, it's an azide, and azides can explode, so I only loaded 2 flakes of potassium azide into a test tube. After carefully heating it to expel all remaining water and alcohol, and strongly heating to decomposition, a flash of potassium vapor was released that coated the interior of the tube. However, as I tried to ampule the potassium under the protection of the produced nitrogen gas, the tube shattered, and the potassium immediately oxidized to this white potassium oxide on the walls. Still, you can see a shiny little bit of metal. Carefully adding water to the piece resulted in a few sparks, confirming that potassium metal was indeed produced. This final section of the video will address how the procedure can be improved for mass production of potassium azide and potassium metal, so feel free to skip it if you want. First, the 60% yield looks bad on first glance, but the hydrazine hydrate preparation step probably has a bad yield since I didn't completely powder the potassium hydroxide and didn't wash the potassium sulfate many times. If I buy 80% hydrazine hydrate instead, the yield should be much higher and closer to 90%. Secondly, the need for large amounts of alcohol for a small yield of azide needs optimization. Thus, after the reflux, the potassium azide produced can be removed by filtration, new potassium hydroxide and hydrazine added to the alcohol, and continue azide production. This can be repeated until the proportion of N-butanol in the alcohol mixture is high enough to not dissolve potassium hydroxide anymore, at which point the mixture can be carefully distilled at low temperature to recover ethanol and N-butanol. An alternative approach uses isopropanol for both making the nitrite ester and as the reaction solvent, hence eliminating the issue of potassium hydroxide solubility, transesterification, and alcohol separation. The process of thermal decomposition and collection of potassium can also be improved, for example by filling the tube with paraffin oil and combining the contents of multiple runs into a single tube to make a large ampule. In the near future, I'll aim to put these optimizations into action and mass-produce potassium azide and potassium metal on the 100-gram scale or more. Thank you for listening, and see you soon.